Hey guys, so in this video, we're going to be going over how to solve exponential and logarithmic equations and inequalities. Just remember when we get to the inequalities part, anytime we solve inequalities, it's done the exact same way as we solve regular equations, except we're going to have, maybe some restrictions, whether things can be less than or greater than or equal to. Okay, so we're going to start by talking about solving exponential functions. So the goal is, if we can, we want to get the same base. So when we start looking at exponential functions and we want to get the variable out of the exponential position, if we notice that the bases can be rewritten in terms of the same base, we want to do that. It's going to make our life so much easier. If not, we'll get to a point where, well, what do we do about that? And basically, it's going to be using logs, because again, remember, logs and exponents are inverses of each other. But if we can rewrite them, we want to do that. So, for example, I have 100 and I have 1 over 10. They both can be rewritten as a base 10. 100 is 10 squared. And remember, anytime we have a fraction, we can write the reciprocal of it using a negative exponent. So we want to bring back those exponent rules. So 1 over 10 is really 10 to the negative first power. By doing that, I now have created the same bases. And if they're the same bases, then their exponents have to equal each other. So the reason behind that is because of this step right here. So if I look in this part, we're actually going to be skipping that when we do solve problems with like bases, because log 10 of 10, or just the common log in this case, will always cancel out with a base 10. So we don't have to write that because of the fact that their exponents will always end up equaling each other. They're just going to drop down. So you'll see as we go through examples in class, I'm not going to be writing out this middle step here. I'm basically going to go from writing them with the same bases down to this point here where I set their exponents equal to each other. So I have a 2 and an x from here, from the square and the x on the outside. I have a -1 and x minus 3 from its exponents. And then it's just a simple algebra 1 solving of equations, right? I distribute, move terms together, combine my like terms, and solve, and I get x equals 1 in this case. Okay. All right. Now, if they're different, which is probably more likely what's going to happen each time, then we just use the logs. Again, we have the application on the calculators. We have the Desmos calculator we're going to use to do this. So it's not the end of the world if we can't rewrite them. Like 2 and 7 are never going to be able to be rewritten to be the same base. But if I take log base 2, I can get it so that this 2 right here goes away, and then the exponent will drop down. So by taking log base 2 of 2, they cancel, the exponent drops down, and then I just have to figure out, well, what's log base 2 of 7? Now, notice I have 3 different things written here, and it really depends on the direction. So you need to be aware of what they're asking you. If they want the actual value, it's log base 2 of 7. That is your actual value. If they want it to show change of base, remember that's when we take the log of the argument divided by the log of the base. So log of 7, log of 2. If they want an estimated value, which for the most part, that's probably what they're going to ask for, then we can just put this in a calculator and find out what it equals. Okay, so log base 2 of 7 is about 2.807. And we're going to round to 3 decimal places just for consistency and for more accuracy. Okay, so again, just be aware of what your directions are asking you. Most of the time, your estimated value is going to be perfectly fine to use. Okay, so let me clear that first. There we go. So we'll be going through these examples in class together. Again, if we can rewrite them, we want to. Like number 4, I can rewrite them to have the same base. If I can't, like in number 5, 1 and 2, Then we're just going to take the log of that. So for instance, for number 2, I would take log base 7 of 7 on both sides to solve it. I do want to go through number 3, just because it has a little bit extra steps involved, right? So I do want to get this x by itself, which means I got to get everything else away. Just like always, move everything else before you can get the variable by itself. So I'm going to start by adding 7. Remember, you always add or subtract before you can multiply or divide. So I have 4e to this power equals 20. Okay. From there, I'm going to divide by the 4, get the e by itself, because the e is what is attached to that exponent. So I have e to the negative 0.3x equals 5. And now I want to get rid of the e, so the exponent will drop down. Well, e is the natural base, so I need to use the natural log in order to get rid of that. And in that case, it's ln. So I'm going to take ln of both sides. I'm going to move myself over here. And we're going to just use decimals. So that's fine. The ln and the e will cancel. Negative 0.3x equals the ln of 5. And that you can put in your calculator. So it's about 1.609. And then at this point, we know how to solve for x. Divide. Okay. And we get x is about negative 5.365. Okay, so really the only new thing now is this part right here, where we're going to have to take the log, or the natural log in this case, of a value to get the exponent to drop down so we can solve for that variable. And we've done inverses, we've done a little bit of solving and simplifying. So we know that the log and the base of an exponent are inverses. They will undo each other, just like up here, the adding undid the subtraction, and over here, the multiplying and the dividing undid each other. All right. So now we're going to get into an application of it. We have Newton's law of cooling. So Newton came up with this formula that looks a lot more intimidating than it actually is, to figure out the time, the temperature of things for cooling purposes. Okay, so we have T is the temperature after some amount of time. T sub 0 is the initial temperature of that item. T sub R is the room temperature, or the temperature of the place that it's in. So whether it's in a room, if it's outside, whatever, it's the surrounding temperature. T is time in minutes, and R is the cooling rate. And the cooling rate is distinguished per item, so it's not always the same rate. Sometimes we might have to find it. Sometimes it might be given to us. Okay, so it all just depends on, the situation at hand. Now, I absolutely love this application because, well, the first example we're going to do is on food, but I'm a big murder mystery fan. I enjoy watching documentaries, there we go, on murder mysteries and unsolved cases and stuff like that. And this Newton's law of cooling is actually very prominent to find time of death. So if they come across a body, they can take its temperature and find out, using all this calculation, to find out the time of death of that person. Okay, and we're actually going to do some examples of that. We're going to start with the food one. All right, so first thing, I'm going to write down the formula again. So T equals T sub 0 minus T sub R e to the negative RT plus T sub R. So we want to find as much of that as we can from the word problem, so we can just fill it in and go with it. So we have our sister cooking her famous chili. She takes it off the stove. The temperature is 212. So that's your initial temperature. Okay. So that's what it's starting at. She took it off the stove. The room is 75 degrees. So obviously that's your room temperature. The cooling rate, we got an R. Perfect. We want to know how long is it going to take the chili to cool off to a perfect serving temperature of 95 75 degrees. So that's going to be the time or the temperature after the amount of time that it's been sitting out for. And we want to figure out the time, obviously. So we're going to fill in all those numbers. So T we said was 95. Okay. T sub 0 was the 212. That's what it started at. We're going to subtract out the room temperature, which is 75 degrees in her kitchen, or the room she had it in. E to the negative R. They told us the R, so that's great. Time is what we're looking for. And then plus the room temperature of 75. Okay, and then from here it's just solving. So it's up to you how many steps you want to do at once. We obviously need to get the 75 over, so we will subtract the 75 from 95. It's going to get us 20. I'm also going to combine the inside here. So 212 minus 75 is 137. And then I have my E value. All right. So again, from here, the goal is to get T by itself. So I can divide, get rid of this coefficient. Okay, I'm going to divide that. Again, I'm going to stick to the 3 decimal place rule. It's pretty, oops, no more E. I don't have any eraser button anymore on this. All right, sorry. So I did need the E. I don't know what I'm doing. Okay, so E and then my power. All right, so now we want to get rid of the E, so we're going to take the ln of both sides. All right, put that in a calculator. Negative 1.924. And then we know we divide, and we get about 37.728. Now they want to know how long will it take. I'm not going to tell somebody, well, it'll take 37.728 minutes. No, I'm not going to say that. We're going to say it's about 38 minutes. And obviously we're going to round up because that 0.728 is higher. Okay. And that's how long it's going to take for cooling. All right, so that's how we can use this application of Newton's law of cooling to figure out how long it will take. So after she's done cooking, you wait about 38 minutes and then you're good to eat for your dinner. Okay. All right. So now we have this next example. So we have, this is our murder mystery stuff, right? Stuff I like. I know some people get a little spooked about it, and if it is something that bothers you, that's fine. Let me know. I can always give you more of the food cooling problems. All right, so I do want to go through this one example though. So we have in this murder mystery, the temperature of the corpse was 90.5 degrees, excuse me, at 1:30, and then it was 86.5 degrees when they took it an hour later. Okay, so that's a time frame that's going to come in important. We have the average body temperature of 98.6, and we have the surrounding temperature of 68 degrees. This was found outside. You've been called in to find out when the murder took place. So in this case, we don't have an R. So it's going to be a 2-step process. Let me write down the formula again. Okay, because I do need to find R. So step 1, we got to find R. All right, and we need to use all the information. So basically, if we want to find R, that means we need to know what T, T sub 0, T sub R, and little t, the time T, is for this. Okay, so when we do this, this 90.5 is going to be 2 things. It's an original temperature that they found, and it's actually a start temperature. Oh, sorry. It's also a temperature after a certain amount of time. We have 86.5, which is a time after, or sorry, temperature after a time frame, after the 1 hour. We have 98.6. This is always going to be the original temperature of the body. And then 68 is our T sub 0. So we have a couple things. We have a temperature after an amount of time. We have a time. Time was 1 hour. And we have, this is actually both original temperature and an after temperature. All right, so first thing we're going to do, find R. We're going to use the 1 hour information for this. So I'm going to fill in everything I know. I know after 1 hour, it was 86.5 degrees. Okay. The original temperature in this case was the 90.5 because they took that first, and then an hour later, they took the 86.5. Okay, the room temperature is 68. E to the negative R. Time is 1. It was the 1 hour. And then again, our room temperature. Okay. Again, as we go through this, we're going to combine our like terms, do what we can. So I'm going to subtract the 68. We get 18.5. Combine those insides. 22.5 e to the negative r. If I multiply these two, 1 times r is just r. And again, we want to solve this. So we'll divide. We get 0.822 equals e to the negative r. We'll take the ln of both sides. That gets us to be about negative 0.196 equals negative r. And now we know our r. So the cooling rate of this individual body was 0.196. Now I can go back and use the original info, move myself over here, in order to find the time of death. Okay, so that's going to be step 2. Find T. And this we're going back to the use original. So I've already used the 86.5. I've already used the 1 hour. I'm not using that stuff anymore. Going back to when they first found the body was 90.5 degrees. Okay, the original temperature of any body is 98.6. Outdoor temperature still 68. E to the negative, I know my rate now, time plus 68. Okay, again, same thing. I'm going to move over my value, my 68. That gets me 22.5. Subtract 98.6 and the 68. That's 30.6. E to the negative 1.96t. Divide that. That gets us 0.735. Again, to get rid of that E, we're going to ln. The ln of this is negative 0.308. Divide. T is about 1.57. Okay, so we need to find time of death. 1.57 is 1 hour, 0.57. It's not 1 hour and 57 minutes. So in order to find what time that actually correlates to, you're going to take 0.57 and times it by 60 minutes. So 0.57 of 60 minutes is about 34 minutes. Okay. You know 0.5 is about half, so it makes sense for it to be over 30 minutes. So 0.57 times 60 gets us gets us 34. So this is 1 hour and 34 minutes that body has been there for, right? Because the 90.5 degrees was the body temperature when they found it, which obviously was after its time of death. So if it's 1 hour and 34 minutes, that is before when they found the body at 1:30. So we need to go back in time. Okay, so I'm actually going to move myself back over here. Let's do it in this section. We have 1:30. I have to go back 1 hour. So if I subtract 1 hour from this, that brings us to 12:30. And this is PM. And then from there, I got to go back 34 minutes. And some people can do this all in their head at once, and that's fine. So 34 minutes from 12:30 is 11:56 a.m. So this is your time of death. So at 11:56 a.m., this person was found to die in any means. They were found at 1:30. We go back in time to find the 11:56 a.m. time of death. So the reason I went through all this is you will be doing a project, or an activity, I should say, on a murder mystery, kind of a clue type game, and you will have to find the time of death and then determine who did it and why, right? Just like the game of Clue. And I'll talk about that more a little bit later on. We'll be doing some more practice problems using Newton's law of cooling with both the food and bodies, just so you get more examples of it before you do get that application. But I think it's a very interesting application of it, very real life, because there are people who have to determine time of death, and they can use it this way. Obviously, science, they can use those methods as well. All right, so let's clear this out. Let's keep on going. All right, so you see there's a whole bunch there. All right, back to solving. So the other thing is that was solving exponents. Now we're going to solve logs. So it's just the opposite way of doing it, right? Before we were taking logs to undo the bases of exponents. Well, now we're going to use exponents to undo the logs. So if they have the same base, or if they have the same log, you can actually just cancel it out. You don't have to even raise it to a power, because you're raising both sides to the same power. And their arguments end up being set equal to each other. Okay. So again, in this case, we have the natural log. So we have to use our natural base, which is e, to cancel them out. If they don't have the same log, that's fine. Then you just raise both sides as a power to the base. So log base 2, I have to make it 2 raised to those powers. So you'll see when I write them, I kind of write it large with the caret underneath it, just so you know that's being raised as a power. So again, the logs are going to cancel with the exponent. The argument falls out, and then you have 2 to the third power. And again, it's just a matter of solving from there. So sometimes you also may need to combine logs. So if you can, bring your logs together, if they're on the same side, bring them together, use those properties that we looked at last week. So if it's an addition problem, we know that it was actually multiplication of the arguments. If it's a subtraction, we know it's a division of the arguments. Okay, and then the same rules apply. Once you get it down to one single log, you can then raise the power and work your way through it. And again, just a reminder, if there is no base, that is a base 10. So this log, I did have to raise to a power of 10 in order to get it to cancel out. A little side note, all logs have to have positive arguments. So if you end up with a value like this one, oops. There we go. Like in this case, where we got 10 and a negative 5, if I was to plug these back in and I find out any of the arguments end up being negative, that's an extraneous solution. So if I plug a 10 in, 2 times 10 is 20, great, it's positive. In this one, 10 minus 5 is 5, it's positive, great. So I know 10 is a valid answer. If I put a negative 5 in, well, 2 times negative 5 is now negative 10. I cannot have a negative argument. So even though it was an answer to the problem I was solving, it's not actually an answer to the log. So always check. And just because you get a negative answer doesn't mean it's automatically invalid, because sometimes you might have a negative number it was being multiplied in the argument by. So always check just to see. You don't have to check the whole thing out to make sure it equals 2. Just check to see if the argument does still remain positive with that number on the inside. Okay. And again, we'll go through these problems together and work through in class how to solve them. Last thing, real quick, is our inequalities. So again, same rules apply. Whether you're looking at an exponent inequality or a log inequality, you're still going to make sure you solve it the same way. You're going to raise it as powers, or you're going to have to take a log of a power to get rid of it, and then you're going to solve it. Now, if it's a less than, this goes back to what I was just saying. You can't have negative logs. So if you're solving a log, and this is only for logs, if you're solving a log and it ends up being a less than problem, you got to make sure you put a cap on the end of it. It has to be between 0 and that number, because we don't want to go below 0 in order for it to get us a negative value. Okay, so just be aware of that as you're going through these problems. Okay. All right, and again, we'll go through working through some of these examples together in class, but again, it's just like always, solving our inequalities are the same as solving our equations. Okay, hopefully it helps. Make sure you ask questions in class.